on the Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Hey everyone, I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, a friend to the universe, and a friend to my co-host.
Yes, it's me. I'm Corinne Caputo, the co-host, and a friend to all. Today we're in a place where I did not make friends a lot.
Yeah, I also didn't make many friends in this space.
Yeah, it's not the place for it.
No, you make friends as you leave this space.
Yes. And I think you can also maybe see other people's screens and then you know who might be a friend in the future.
That's why you sit in the back.
Yeah, exactly. We are in a lecture hall, a classic college lecture hall. A class is just filing out, and then we'll have it to ourselves. But this seemed like a place to learn the serious stuff.
Yeah. It's especially helpful. There are chalkboards in the front of the room in case we want to write down equations or any diagrams. And it just has that old nostalgic feel, you know, like the wooden seats with the little desk thing that comes down and it smells like chalk and it's really echoey and it's cold.
Yeah.
It's so cold all the time.
I was going to say the temperature's never right and maybe it's to keep me awake, but there's something about it that's not super conducive to me for learning.
Yeah. But no, I have had very satisfying memories in spaces like this. I think that's how I'm going to put it. Because it is satisfying to struggle to learn something.
Yeah. I've been thinking about that specifically of at work or things, or just like in general, when someone kind of wants to do something the way they've always done it. And I'm like, no, it actually feels really good for your brain to do something new.
Yes. Yeah, to challenge yourself and rise to that challenge.
Yeah.
So, well, thank you for bringing us to a lecture hall.
Of course.
And listeners, today, the very sciencey topic that we're going to be talking about, maybe the most like sciencey topic that we've covered so far.
I mean, it sounds the most sciencey.
You're right. It does. So today we're talking about the field of science called thermodynamics. Many physicists, many engineers, many chemists have to take a class in thermodynamics because it is a really wide-reaching field that has its fingers in lots of disciplines. So today we're just going to be covering the basics of thermodynamics and some of its consequences and where you interact with it in daily life. But Corinne, what does the word thermodynamics sound like it means to you?
It seems like something about the interaction of temperature. I want to say heat, but because thermo is like a heat word for me, but I guess it could also be cold. And dynamics is like the relationship and interaction of those things.
That's fascinating. But dynamics means like the relationship between things because you're thinking of like interpersonal dynamics.
Yes.
Yeah.
Yes.
Okay. Fascinating. Because in my mind, dynamics means the motion of things.
Ooh, I do think of dynamic as motion.
Yeah. Like we both did like a body roll, essentially, listeners. So I thought that this would mean the field of science having to do with how heat moves, but I looked up the etymology of thermodynamics and it comes from the Greek thermo meaning heat. Yes, so we're both right there. And dynamics comes from a word that means force or power.
Ooh.
So this field deals with heat and energy, and it asks the questions, how does thermal energy convert to and from other forms of energy? So how does thermal power convert to and from other forms of power? And how does that conversion, how does the behavior of thermal energy affect matter?
Okay, cool. I will put aside my hope for a relationship story.
I'm sure that you could write like a romance story with thermodynamics at its core. You know, scientists fall in love too. We're people. You're
so right.
And Like we did with our fluid dynamics episode where I just nerded out over my favorite class that I took in grad school and told you about some of the real world applications, I wanted to do that for thermodynamics, but the applications are so wide reaching, Corinne. Pretty much anything that has to do with heat has to do with thermodynamics. So air conditioning. You know, it's about to be summer here in the Northern Hemisphere. Air conditioners rely on moving air from one space to another. They condense it, which changes the pressure and therefore the temperature. So air conditioners rely on really cool thermodynamics science. So we're going to be thinking thermodynamics in a couple of months. Even within ourselves, like the way that our bodies regulate temperature, I think you could even say that our metabolism is a form of thermodynamics, the way that we convert energy from food into heat and energy that we use to move. Like that's all thermodynamics. There's so many different applications of it. Like right now I can hear the fan in my laptop whirring and that's to like regulate the temperature inside of that.
Oh, I haven't thought about that. I always think of my fan. It's nice to think that there's more of a reason than my computer is just ready to fly away. That's how it seems.
Yes, it does actually serve a purpose. It's not just
like I know that it's to cool it off, but I'm just like, this little fan's never going to work. So get out of here.
I know. I am often surprised that it works because it can't be that big.
No.
And yet my computer has never once caught fire.
Thank God.
Knock on wood.
I did pull my computer out of my backpack the other day and it was so hot and the fan was on and I was like, oops, I guess I should be shutting this down.
Yeah, it's getting to be that season, folks, where you want to look out for your electronic devices. They do not love the heat. Corinne, have you ever experienced like a thermodynamics class or lesson? Like what?
Not me ever. My brother did. He had a thermodynamics textbook that I would see a lot, and he's an engineer and like works with like heating and ventilation and AC systems. So this is, I imagine, his life's work. But I have never touched the stuff.
The twin mind meld doesn't extend so far to career choices. And
I think if we were to figure out how to do that, I would not reach for this information first.
All right, you're right. Yeah, because you have me to teach it to you.
I don't need it.
You don't need the twin mind meld. You have to use that. You only have a limited number of uses.
Exactly.
Thermodynamics was a required course for astrophysics majors in college, but I took thermodynamics for engineers instead of thermodynamics for physicists. That was my little, shortcut.
I was going to say, that was on purpose, or was that a mistake?
It was on purpose because the thermodynamics for engineers was more applied and also had a professor with a better reputation than thermodynamics for physicists.
That could make a huge difference.
Yeah, and I imagine that the thermodynamics for physicists dealt a lot more with statistical thermodynamics, which I'll talk a bit more about later, but I wanted something that was more applied and less math heavy. By applied, I mean like hands-on. I think I actually got to go into the engineers' labs and we did some things with machinery, which was pretty cool. And our homework problems were all about like calculating the BTU, like how large of a space can an air conditioner actually cool down. And it was very practical, which I appreciated. But that class was still so hard. But I really struggled in a lot of my physics and math classes in college.
I struggled with my math classes too. And I was good at physics and math in high school, but like it just didn't always translate the more advanced I got.
Yeah, I felt very stupid when I started college. After I started taking classes, because I was far behind a lot of my peers. But I don't know. Look, it worked out.
Look at you now.
Yeah. So I haven't had the best experiences with thermodynamics, and Corinne's experience is an intimidating textbook of her brother's. So let's get into it and hopefully make this field seem less intimidating. So starting with some history so that we know where the field came from, I think that'll help us get some context. I'd say the history of thermodynamics can be traced back to the 1600s. That's when we were starting to learn about the relationship between temperature and pressure and volume. There was a physicist. His last name is Boyle. Eventually, he came up with a law called Boyle's law, which states that pressure and temperature are inversely proportional to each other. So if temperature goes up, then pressure is going to go down. And if the temperature goes down, then the pressure is going to go up. It's very important for meteorologists and low versus high pressure systems. Mm-hmm. Yeah. But this knowledge eventually led to the invention of the steam engine. And that led to the Industrial Revolution. And so people wanted more and more efficient steam engines. And to do that, they needed to understand how energy and heat work together. So basically, the field of thermodynamics got its big push because of industry and capitalism.
Always is, right.
Always is. There are a few people who are really instrumental in discovering different laws in different parts of thermodynamics. So here are a few of the big names that you should know if you want to know about the history of this field. In around the 1810s into the 1820s, there was a French physicist known as Sadi Carnot, and he is called the father of thermodynamics. In 1824, he published the first. It's a treatise, which is separate from a book, and also separate from an essay somehow, but it was the first thing that was published about thermodynamics. And the translation of the title is Reflections on the Motive Power of Fire. They actually weren't calling it thermodynamics at the time. That wouldn't come until, a few years later. But he was an engineer, and he was working with the military to create machines, and he was interested in how fire and other hot things motivated or moved other things.
Cool.
Yeah, it is cool. It was 1824. And then I'd say the next person who you need to know in thermodynamics is this Scots-Irish physicist named William Thomson. And very few people know his actual name because he's better known as Lord Kelvin.
Of Kelvin?
Of Kelvin, yes. Of the Kelvins, of the temperature Kelvins. Exactly, Corinne. Lord Kelvin is a title. He was the first Baron Kelvin. So he was the first of his name. And Kelvin is named for a river that runs by this dude's laboratory in Scotland. So he was ennobled in 1892. He was named Lord Kelvin in 1892. And it was before that he did a lot of his really cool thermodynamics work. So he did the work as William Thomson, but we all remember him as Lord Kelvin.
What a name.
His name was just forgotten. I kind of feel bad for him. Yeah. He was the person who named it thermodynamics. I don't remember when he wrote this, but he wrote it originally as an adjective, like the thermodynamic process with a hyphen in it. And then thermodynamics became the field's name that he gave it. But in 1854, he gave the field a definition. He defined thermodynamics as the subject of the relation of heat to forces acting between contiguous parts of bodies, contiguous meaning the parts of the bodies that touch each other, and the relation of heat to electrical agency. So that's a pretty wide definition, but it was the first kind of concrete consolidation of all of the work that people had been doing in this field for a little bit. And then another name that you should know in thermodynamics is a German physicist named Rudolf Clausius. In 1856, so just a couple years after Kelvin defines thermodynamics, Clausius named a new term that we are still very familiar with, entropy. So in 1856, he says that entropy is a thermodynamic quantity. People had been talking about it before, but they were calling it the equivalence value or the transformational content of some system or some body. So he gave it the name entropy, and that was very important because this guy, Rudolf Clausius, was one of the scientists who came up with actually a couple of the laws of thermodynamics.
Ooh.
Yes. Before I get into the laws of thermodynamics, do you have any questions about how it works?
I mean, yes, because I don't know this topic at all, so I am a blank slate.
Okay. Let's go through the laws, and if anything is confusing, let me know, because this is a big episode, and I don't want to use equations or anything, but I will say that a lot of these equations look really simple when you write them out. Like some of these equations look as simple as like H equals U plus P. Like that. Sure. They make it look so simple.
It's like, oh, that makes sense. And then H is like 40 things itself. Yeah.
But I do like this because this field is wide-reaching and it can get really complicated, especially when you're dealing with the statistics of it. But at its core, it relies on a few basic concepts. So we're gonna go through those basic concepts. Those are the laws. There are 4 of them. We start with the 0th law. This was actually added later. This was added after discussions in the 1930s, and it was added as kind of an obvious but necessary for thoroughness claim after the other laws had already been kind of written down and officialized. And so the 0th law of thermodynamics says that if 2 systems are in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other.
Yeah, so, that makes sense to me.
Yes, it's very obvious. This is the equivalence law. Basically, if A equals C and B equals C, then A equals B.
Yep. Perfect. Okay.
Yeah. But this does introduce an important concept of thermal equilibrium. Thermal equilibrium is when 2 systems or multiple systems are no longer exchanging energy between each other. So thermal equilibrium happens when your coffee cools before you drink it because it reaches thermal equilibrium with the air around it.
Sure. Okay. Yeah. That makes sense.
That's what happens when your water freezes in the freezer. Like that's because it is reaching equilibrium with the temperature around it. So thermal equilibrium is a fascinating state where it's more balanced, and you can treat the 2 systems as one.
I like a balanced picture.
Yes.
I don't like when my ice melts in my coffee, but I like the principle behind it.
I like the principle too because it shows that nature just wants things to merge and become one. I literally wrote in my notes, thermal equilibrium, no energy flow between states. They are one. They are one with each other. But this also tells us what temperature is. Temperature is a measure of the average kinetic energy in a system, so the average energy from motion that a system has. If the molecules in a space are moving very quickly, then the temperature is higher. And if the molecules are moving very slowly, then the temperature is lower.
Okay, sure.
Yeah, this is like the gas versus solid thing, where gases exist at higher temperatures and their molecules are moving fast and freely, whereas solids exist at lower temperatures and the molecules are packed together and they don't move very much. And then we go to the first law. The first law of thermodynamics says that when you have a system and you're not transferring matter into or out of the system, then energy cannot be created or destroyed. It can only be transformed from one form to another.
This one I did know.
Yeah. Yes.
Yeah.
The whole energy can't be created or destroyed thing.
Yeah, this is one of those famous ones.
It is. This is the famous one. One of the famous ones. The interesting thing about these laws is that they weren't. It's not like Kepler's laws or Newton's laws where one person like wrote them down over time and so they were formalized somewhere. Yeah. These were added to over many decades.
Yeah.
And so there are lots of different wordings for these laws if you go to different sources. One way to say the first law of thermodynamics is energy can't be created or destroyed. Another way to say this is that the change in a system's internal energy, the grand sum of all the energy in the system, the kinetic energy from motion, the potential energy from chemistry or gravity, all of the different types of energy that you can have in a system, you add that together, that's the internal energy. And that is the change in that internal energy is equal to the energy that the system gains from heat minus the thermodynamic work done by the system. So if the system evaporates any water, or if it moves something to a different location, or if the temperature changes, like something, like if the system does any type of heat-related work, you have to subtract that. Another way of saying that is that the net heat supplied to the system equals the net work done by the system. So if you're putting any heat in, then something has to be done with that energy. Or if you're doing anything, the energy for doing that had to come from somewhere.
Right.
Yeah.
Okay.
Yeah. I said that in a lot of different ways. Are any of them helpful?
I think the last one of like, if I'm doing something, this energy came from somewhere. It's not coming from nowhere or going nowhere.
Yeah. And there are all sorts of caveats with the thermodynamics laws, because this is specifically, if matter isn't moving in or out of the system. The system has to be closed. The system has to be able to reach some sort of equilibrium. So there are all sorts of caveats around these laws.
Hey, it's Corinne. I want to give a quick thank you to our patrons, as always. So thank you to our Sunlike stars, Lissa, Scott Reynolds, Ian O'Leary, Augustin, and Tom T. And of course, you can support us and hear your name on the show and make it to our patron star chart, all by supporting us on Patreon. It's just about $1 per episode. And if you sign up for an annual membership, you get a 13% discount. You can find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to patreon.com/palebluepod. And if you can't support us financially, as always, that is fine. We love you very much. You can please review the show on whatever app you use and share it with your friends. And I also have a podcast recommendation for you. Join the Party. Join the Party is an actual play podcast with tangible worlds, genre-pushing storytelling, and collaborators who make each other laugh each week. DM Eric and the emphatic players Amanda, Brandon, and Julia welcome everyone to the table, from longtime TTRPG players to folks who've never touched a role-playing game before. You can hop into their current campaign, a pirate story set in the world of plant and bug folk, or marathon completed stories with the Campaign, a game set in a weird summer camp. There's Campaign 2 for a modern superhero game, and of course Campaign 1 for a high fantasy story. And once a month, there's the After Party, an episode where they answer your questions about the show and how they play the game. So what are you waiting for? Pull up a chair and join the party. Search for Join the Party in your podcast app or go to jointhepartypod.com. And finally, I have a really exciting offer for cat owners. Litter Robot is the solution to all of your litter box problems. Never scoop again with Litter Robot. I don't have a cat, but my brother does, and I have taken care of it maybe a handful of times. Ollie, he's so cute, and he's kind of a menace. But the idea of never scooping a litter box again, that sounds amazing. Litter Robot's self-cleaning technology automatically cleans after every use, so your cats will always have a fresh bed of litter to do their business, and your friends won't think your house smells like a litter box, which is amazing. And get this, Litterbox will send a notification to your phone when it needs to be emptied, so you never have to remember again if it's time to check. It gives you data and insights to stay on top of your cat's health, and it's easy to set up. There's a weight sensor that automatically cleans, so you can set up how long the robot waits before it starts a cleaning cycle. So as a special offer to listeners of the show, go to stopscooping.com/palebluepod and enter code palebluepod to save an extra $50 on any Litter Robot bundle. That's an extra $50 off any Litter Robot bundle at stopscooping.com/palebluepod and enter the code palebluepod at checkout. Okay, back to the show.
Law number 2. Are we ready for law number 2?
Oh, yeah.
Okay. I think you're going to recognize it. It will sound familiar to you.
Okay.
So the second law of thermodynamics, one way to say it is that the entropy of an isolated system tends to increase over time.
Okay.
Another way to say this is that natural thermodynamic processes result in more disordered states over time, meaning they result in states that are more varied or more complex or more random. So basically, this is saying entropy basically always increases in a system.
And the entropy, again, is like the kind of, I want to say chaos, but like the randomness of it.
Yes. I have not yet defined this new term that I have introduced. Yes. Entropy is a measured quantity. It's the chaos of a system or the randomness of a system. If you're looking at the equation for it, it's the thermal energy that a system has. So all of the energy from heat divided by the temperature, the average temperature of the system. But it is, a lot of people for shorthand say that it's a measure of chaos in the system, which really means statistically, it's a measure of how many different possible states the system can have, or how many different possible arrangements can the system have. A system that has 5 molecules of oxygen in it has fewer potential states than a system with 10 oxygen molecules in it, right? Just because there are more ways that those 10 molecules can be arranged than the 5 molecules in the other system.
Right.
Yeah.
So this law says that increases over time. The longer it's around, or the longer we're looking at it too, the entropy increases.
This says that processes increase entropy over time. So if nothing happens, entropy doesn't have to increase. Or if something happens, but it's reversible, you can undo it, then entropy doesn't increase. But if anything happens in a system that can't be undone, then by definition, entropy has to increase.
Sure. Okay.
This second law was formulated by a couple of people at the same time by the German Clausius, who coined the term entropy in 1856, and also our buddy Lord Kelvin. He was one of they were the two people who independently came up with the second law. And I don't think I said it, but the first law was also thought of by multiple people independently. There were at least 4 of them. There was a German named Mayer. There was a German named Helmholtz, who has a constant named after him. So he did a lot in science. There was someone named Colding, and then there was someone who I think is French or maybe Belgian named James Joule. His last name Joule, is the unit that we use for energy.
Yes.
In some scientific disciplines.
That.
So he also did stuff. But yeah, the 4 of them together did the first law.
What a crew.
Yeah. So the second law, also multiple people came up with it at once. And that also means that they worded it in their own ways. And I thought it was really interesting to see how the wording of the second law changed over time. The way that Clausius puts it at first, Rudolf Clausius, I think it sounds very different from what it ends up being. So Rudolf Clausius, when he first comes up with the second law of thermodynamics, he says, quote, "Heat generally cannot flow spontaneously from a material at a lower temperature to a material at a higher temperature." So that's the first phrasing that we have of this law. And that means that right off the bat, when we're first getting this understanding of thermodynamics, the first thing that they see is a direction of causality. They see that you can go in one direction, but not the other. You can go, the heat in a system will go from the higher temperature thing to the lower temperature thing, but not the other way around.
Yeah, okay, that makes sense.
Yeah, so from the beginning, the second law of thermodynamics has this preferred directionality to it. And then Lord Kelvin comes along, and he says that it's impossible to convert heat in a completely cyclical process. So you can't have heat going in one direction and then circling back and going the other direction. It can only go in one direction. So we have these 2 people who came up with the second law of thermodynamics, and they both emphasize the directionality of the second law of thermodynamics. They say that when you observe the natural world around us, you see processes happening. You see liquids evaporating. You see machines moving on cogs. You see friction happen. You see all these processes around you. And all of those processes make a change in the world that is noticeable and can't be undone. And we can calculate how that change adds to the chaos or randomness of the system. And that change is entropy. That's what they figured out. And we had a question from one of our listeners who emailed us. Nebulous Natalie emailed us asking about time and if we could do a whole episode about time. And I don't think we could do a whole episode about time, but one of the explanations for time comes from the second law of thermodynamics. So it was actually your question, Natalie, that inspired me to want to do a thermodynamics episode in the first place. The second law gives rise to the arrow of time because it creates the idea of linearity, that there's a sequence of cause and effect that you can track. Because if entropy is always increasing, it's always going in one direction, then you can tell a before and an after. There's a Nobel-winning physicist, Frank Wilczek, who wrote about time, and I included an interview he did about time in our research notes for patrons. And he says that the second law of thermodynamics gives rise to, quote, asymmetries between the future and the past, which I really love, because there is a quantifiable difference between the past and the future if you're looking at the amount of randomness in your system.
Sure.
And then the third law of thermodynamics was added much later in 1906. So we're talking 40, 50 years after the first two laws were postulated. And so the third law, which is really the fourth law because we started at zero, says that as the temperature of a system reaches absolute zero, all processes in that system will cease, and the entropy of the system approaches a minimum value. Not zero, but a minimum value. And absolute zero is this like theoretical temperature that Lord Kelvin came up with. It's 0 Kelvin. We use that temperature scale because Lord Kelvin came up with it. And absolute zero is this theoretical temperature where all molecular motion and all exchange of energy stops.
Okay.
Yeah.
Feels bad.
Yes. That would be bad, but it's also seems to be impossible, practically speaking. So in 1906, a German physicist, Walter Nernst, he came up with the third law of thermodynamics. The way he put it was, it is impossible for any procedure to lead to the isotherm T equals zero, so to lead to absolute zero, in a finite number of steps, saying that you need an infinite number of steps to reach absolute zero. Okay. Basically, it's impossible.
Yeah, so that's never going to happen.
Yeah, there will always be energy in the system, but you can asymptotically approach absolute zero where you keep getting closer and closer and closer to it. Those are the laws.
They kind of make sense. Or they do make sense to me. My day-to-day life does not apply these. I experience them, but I'm never thinking about we should put words to why that's happening.
Yeah, a lot of it does seem like they're using unnecessarily fancy science jargon to explain really obvious stuff you see.
Yeah, but somebody had to start. Someone had to do it. Yeah.
Exactly. It's like the person who defined the difference between a triangle and a square. Someone had to do it.
We had to do that so we could build on it. And I appreciate the work.
But there also is so much that we can do mechanically and technologically once we have an understanding of how heat moves through a system.
True.
So much. Yeah. I have some examples of stuff that we're actively working on now, because thermodynamics isn't just a field of study from the 1800s.
Of course not.
we're still doing stuff. But I do want to call attention. I have here in my notes that there are these two words that often get brought up with thermodynamics. One is entropy, which we talked about. Another is enthalpy. Have you heard of enthalpy?
No, I don't think I have.
I remember, I think, a high school physics teacher really harping on this difference for one day. Entropy is a quality of the system. It increases over time, and it comes from the second law of thermodynamics. And it's the thermal energy in a system divided by the temperature of that system. Enthalpy comes to us from the first law of thermodynamics, and it is a measure of the total heat present in the system. So when you're calculating the system's thermal energy, you can then also calculate its enthalpy, they are related.
Okay.
That's for the engineers and the physics students out there.
Yeah.
Okay, so now some cool modern thermodynamics research. There are a few broadly accepted fields, subfields of thermodynamics. So there's the classical thermodynamics or the macroscopic thermodynamics research, which looks at things on big scales with big systems. So galaxies, or even universes. Like how does heat get transferred into and out of those really big systems? Or even like macroscopic can be things on human-sized scales too. Like it can be the like air conditioning stuff is macro thermodynamics. And then there's statistical thermodynamics, which is dealing with probabilities and like really large number molecule counts. Like they're looking at the like what are the probabilities of the different arrangement states for like millions of molecules. It hurts my head to think about statistical thermodynamics, and so I won't.
That feels hard. Yeah, that feels like a very specific field.
But it's useful in a lot of things because molecules are everywhere, and there are complex states everywhere. Like, I guess it doesn't have to necessarily just be about like molecules, but they're dealing with systems that aren't spatially large, but have enough things in them that you can do large number statistics.
Yeah.
That was not covered in thermo for engineers. We did not.
They couldn't get to that.
It wasn't even on the syllabus, Corinne. Like they were just like, you do not need to know this.
We're not touching that.
But it would have been in the thermodynamics for physicists class.
Yeah. So, okay, that makes sense.
Yeah, I said nope. I said not today, statistics,
not
Satan.
For me.
And then there's chemical thermodynamics. So they study how heat is produced or used or transformed or transferred in different chemical reactions. Okay. And there's a lot of overlap and, they work together, but they're all useful in a wide variety of subjects. So now a few like specific things that we're doing with thermodynamics research. A lot of really useful applications in climate change and in figuring out how to deal with that.
I hadn't thought about that. Sure.
Because climate change is heat. And so studying thermodynamics on these macro scales can help us figure out how to develop heat sinks, how to develop materials that can better reflect the sun's light and heat. Or one article I found was about researching ways to keep electrical equipment cool in times of overwhelm. So like, the fans and the laptops, but on much bigger scales. That article was about the Texas electrical grid.
Yeah.
Yeah. And as people start using air conditioning more because of climate change, we're going to need ways to cool down those electrical systems and make sure they don't overheat, which I don't think is irony.
No.
That's not irony. That's just like how it, how like no one actually knows what irony means?
I know.
Like
I'm the worst at this.
Yeah. That's not irony, but it feels like it should be.
It's the feeling. It's the feeling of that. You know what that conjures.
Yeah. Another article I found talked about a new equation or a new method to measure entropy, but on nanometer scales. So going from the macro to the nano.
Tiny.
Very, very tiny. They're essentially shining lasers at materials and then calculating the entropy of that thermodynamic process. Like the thermodynamic process is shining the laser at the material. That creates some sort of change in the material itself, like in the system of the material, and they can calculate the entropy on that using really advanced and fine-tuned computer models. It's actually really interesting that they can measure entropy on such small scales, but also short time scales because the laser beams are like very, very fast. And I think once we know more about entropy on those small scales, maybe it probably has like quantum applications. I feel like everything small has quantum applications. And then another article that I found talked about a 2023 study out of West Virginia University. And it said that researchers at WVU had expanded our understanding of the first law of thermodynamics. So currently, or I guess before they did this work, the first law of thermodynamics only applied to systems that were in equilibrium or could reach equilibrium, but not all systems can achieve equilibrium. Like there's always going to be some turbulence or some change in the system or some exchange of energy, like in really, really hot plasmas out in space, like in the cores of stars and stuff.
Right.
And so these researchers were studying entropy in those non-equilibrium environments, and they like developed a new model to figure out how those systems work. And it gave us a way to measure the energy in all sorts of generalized non-equilibrium systems.
Oh, cool. I never thought about how somebody couldn't reach equilibrium.
Yeah. There aren't many states.
Yeah.
There aren't many situations like that, but there are some. And there's an energy inherent to like not being in equilibrium. I guess there's an energy inherent to like a potential to find that equilibrium. And now they have figured out what that inherent energy is.
And that was just last year. Wow.
Yeah, we're still learning stuff.
Love it.
How does thermodynamics feel now, Corinne, to you?
I mean, it feels very broad, but a lot of applications. And I like thinking about how I experience it day to day. Like, you know, putting ice in the freezer or putting ice in my coffee and why those things are changing states. I can't see me ever using these formulas or this. And I can't see me taking this course. However, the textbook is slightly less scary.
I'm glad. Would you take a course in laws that we came up with? Like if we came up with the laws of pale blue thermodynamics.
Yes.
Would you read that book?
Yeah, that I might take.
Okay.
That I would bet is even more confusing, but I'm in. I'm willing to do the work.
Yeah, I don't know if I can trust those researchers, but I definitely, my interest would be piqued.
Yes, I'm listening.
Okay. All right, well, now we have to come up with the laws of pale blue thermodynamics.
Okay.
These laws are what we think have to do with like heat, energy, and the exchange and transformation thereof.
What I'm thinking has nothing to do with heat, but it's the language of these laws.
Oh,
which
great.
is just, you know, when pale blue pod goes up, then being scared of the universe goes down.
Yes. Let's call that the law of inverse intimidation proportionality.
That's perfect.
Great. The law number one, as pale blue pod goes up, scarediness of the universe goes down.
Bravery goes up. But I guess we want the
acceptance.
Yes.
Yeah.
That's the word.
Yeah, it's actually listening to Pale Blue Pod and acceptance of the universe are proportional.
Yes.
Yeah.
Okay. There's a lot of ways to look at this law. And that's for the next, 10 generations of scientists to define. Keep adding to it.
You're right. Science is an iterative process. Yeah, that's law number one. Law number two is kind of in line with entropy. Maybe as time goes on,
the more episodes we do, the more random the topics will get.
That's true. I feel like we need something that's as obvious as the zeroth law of thermodynamics, like a lot of equivalents for Pale Blue Pod. So something like, if you listen to Pale Blue Pod and your friend listens to any smart podcast, then your friend would also like Pale Blue Pod. If you like Pale Blue Pod and you like your friend, then your friend would also like Pale Blue Pod.
I like that.
That's the zeroth law of Pale Blue Pod.
That's the new marketing tactic.
Yes. Okay, and then a final law, kind of related maybe to the third law of thermodynamics about reaching absolute zero, is that it is impossible to have zero interest in space.
Ooh, I like that.
Because even if you think you're not into it...
I think it's impossible to have zero interest in, almost anything.
I disagree.
But especially space. Oh,
there
really?
are things I have zero interest in.
I mean, I guess I'm just assuming there's got to be one cool fact about that.
I mean...
I have zero interest in some television shows, so I do take it back.
Yeah.
There's things that I'm like, that's not for me.
Yeah, there are things that I don't care about at all, but I think everyone cares at least a little bit about space. Like if you've ever, worn sunglasses.
Yes. I mean, that's what was so fun about working at the Space Center. It was like, there's so little work for me to do. You're coming in excited.
Well, there we have it. We have our 4 laws of thermodynamics.
Love it. I'm signing up for that course.
Yay. Okay, we'll teach it in this lecture hall.
Yay.
It's going to be next semester, every Tuesday, Thursday, starting at 10 a.m. There will be a class stretch in the middle of the lecture. But for now, we have to go and register with the admin office to make sure we get the space.
We get the seat. Yeah, you're so right.
Yeah, but whether you register for the class or not, I mean, you should register. What are you thinking? But if it competes with something else that you need to have on your schedule, like another requirement for your major or something, we understand. That's okay.
Yeah,
you're still space.
You're still space.
Bye. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.